So our exponential function, let's draw up the graph, the basic exponential graph. There it is. So it's never negative, of course, because raise a positive number to a power, you're still going to get a positive number. And as we know, a to the power of 0 will always be 1. So it always has a y-intercept of 1. This is assuming the base is greater than 1, of course. Base was in between 0 and 1, then it would flip vertically, because essentially what you're saying is a to the power of negative x. Because if it's between 0 and 1, you're going to have a fraction. And if you turn the fraction upside down, now you get a base bigger than 1 again. And so it's the same as the a to the negative x. So it could be that actually the red one is a to the negative x when the base is in between 0 and 1. And the blue one could be a to the negative x when a is greater than 1. So just keep in mind what the base is. But the standard one we usually see is that red one where the base is bigger than 1. So a to the power of x. Now, we can look at that and say, well, the domain, all real x, you can always substitute a value in and get an answer. The range, however, as I just said before, well, we're only going to get positive numbers. So y is greater than 0. We're actually really interested in not just a to the power of x, but more specifically the number e. So e is another irrational number, like pi is an irrational number, it goes on forever. We don't know its exact value. Well, same with e. That's the actual definition of e. The limit as n approaches infinity of 1 plus 1 on n, all to the power of n. So as you substitute in bigger and bigger numbers, you'll get closer and closer to the value of e. But as it is an infinite sum, that's what's making it irrational then, because of course it keeps going and changes as those values of n gets larger and larger, so you never actually reach the final value, the exact value. If you hit it on your calculator, it looks like it does repeat. But that's because of the screen size of your calculator, what it can handle. So it starts off at 2.718281828. So it looks like it is a repeating decimal, which of course you could write as a fraction. If our screen was longer, then we'd see the digits do indeed change. Maybe on a spreadsheet or something like that where you've got more room, you'd be able to see that, because you get more decimal places on a spreadsheet than a calculator. Just as a quick example there, so the E button is the same button as the natural log button, because remember natural log is base E, so you have to hit second function or inverse or something like that, I think, don't you, to get E to the power or something. We're interested with all our functions, how do we differentiate them, how do we integrate them, so we can then go and use these functions in our applications of calculus. And as I mentioned to you while we were doing that quiz, to differentiate an exponential, it's the world's easiest derivative. If you have e to the function x, you differentiate the power and you just put that out the front. What you've got to be careful with though, because with polynomials, remember, you subtract 1 from the power. So be careful you don't subtract 1 from the power for these ones. With exponential, the power stays the same. So you just differentiate whatever function's in the power, that answer goes out front, and then times the original function, e to whatever the function was. What happens if the base is not e, so it's something else? It's still the same, so I still differentiate the power, but I also multiply it by the natural log of the base. Because essentially you're just using your change of base rule, because we can differentiate the natural base. So in that one step, what was actually done, I guess, is change the base of the question, then differentiated it. But rather than doing that each time, we know it's always going to end up, that pattern will always be, actually we just end up multiplying by the natural log of whatever the base is. So the world's easiest question then, if y is e to the x, then the derivative is e to the x. Differentiate the power, you get 1. What's that actually saying to us? If you remember what the derivative measures the slope of the tangent. So that is why, if you think back to our exponential curve, starts off shallow and gets steeper and steeper and steeper, because at any point the slope of the tangent is going to be equal to the y value. That's what they're basically saying. So as that graph's going up and up, it's getting steeper and steeper and steeper, and that's our exponential curve. So e to the 5x, differentiate the power, put it out the front, we get 5e to the 5x. 4x plus 3. So linear functions are nice and easy. It just turns out to be the coefficient of x goes out the front. Of course, it doesn't have to be linear. There's a quadratic function, but again, differentiate 2x plus 3. As you see, I've put it in parentheses there. Otherwise, we'll make the mistake of thinking it's just 3 times it, but no, it's 2x plus 3. It's all times it. Well, calculus rules that we saw before. So product rule. Write down the first, 3x squared. Diff the second, 4e to the 4x. Plus, write down the second, e to the 4x. Diff the first, 6x. Tidy that up a bit. Factorise it. I guess it depends what you're going to do with the derivative, as whether you bother factorising it or not. I suppose the most common thing we do with the derivative is find those stationary points. When is the tangent horizontal? So in that case, we'd want it to be factorised because we're going to solve the equation when's the derivative equal to 0. And when we're solving equations equal to 0, we always factorise them first. Chain rule, anarchy. Bring down the power. 7, lower the power. 6, diff the inside. We get 3e to the 3x. So just tidying that one up, end up with 21e to the 3x, and so on. Quotient rule. Square the bottom. Write down the bottom. Diff the top. Minus. Write down the top. Diff the bottom. Be very, very careful. Remember your index laws. It is so easy to make the mistake of going e to the x times e to the x is e to the x squared. Remember, we add the powers, and of course we get e to the 2x. And in this case, the e to the 2x's cancel, and we end up with 3e to the x over our e to the x plus 3 all squared. I guess one of the first questions we saw in calculus was, how do you find the equation of a tangent? So we're going to find the equation at the point 1. Now the exact value of the y value at that point would be e squared plus 1. Don't know what it is exactly because we don't know what e is. So we'll leave it as e squared plus 1. Find the derivative. The derivative, of course, is the formula that allows us to find the slope of the tangent. Substitute in 1. So we know the slope of that point is 2e squared. Point slope formula, y minus the y value, e squared plus 1. Slope 2e squared outside of x minus 1. And then expand out. I put it in general form. Now, be careful. The sort of mistakes I see with this sort of question is, for the slope, people substitute in the 2e to the 2x rather than subbing in the x equals 1. So be careful with that. Make sure you actually find the value of the slope. Y equals 4, so the base now is not e. Okay, that's cool. We said we can handle that. All we do is differentiate it like before, but we also multiply by the natural log of the base. And you'll notice I put log 4 in parentheses because I thought it would just be so easy to muck that one up, and it would look like 44 to the power of x squared or something like that. And if I put it out the front and went log 4 times 2x, it would look like log 42x. And so I've put the log 4 in parentheses to make it clear that this is an individual thing that we're multiplying it by. So y equals log x. Hang on, we saw how we did that before. But now we know how to differentiate exponentials. We can actually see, well, why is it? When we differentiate log x, we get derivative on function. If I rewrite that and make x the subject, so to undo the log, we exponentialize, if that is such a word, and I'll find dx to y. I'll differentiate x with respect to y. But when we differentiate e to the y, we get e to the y. So therefore our derivative, dy dx, would be 1 over e to the y. But hang on a sec, x is e to the y. So if I want that in terms of x, there it is, the 1 over x. So that's why we get that interesting answer of differentiating logs. Log disappears altogether. We just end up with derivative on function. Okay.